Hello all, welcome to the Microwave and Radar Engineering Lecture 7. At the end of this lecture, you will be able to derive the general solutions of TM, TE and the TEM waves and analyze the propagation of waves in a rectangular waveguide. So let us first discuss the propagation of the waves to obtain the general solutions. As we know, the Maxwell equations are del cross E is equal to minus j omega mu of H and del cross H is equal to sigma plus j omega epsilon of E, where E is the electric field and H is the magnetic field in the directions of X, Y and Z. For non-conducting regions between the two plates or for simply source-free regions, the value of sigma is 0. So our del cross H equation is now reduced to only j omega epsilon of E. Solving this equation, on the left hand side we will get a matrix to solve the cross of del and H, and on the right hand side we can expand our electric field in the form of Ex, Ey and Az, where it is in the directions of Ax, Ay and Az. Also, we are propagating here in the z direction, so we can substitute curly by curly z as minus of gamma, where gamma is the propagation constant. Now, solving and equating the coefficients in this equation, we will get the coefficient of Ax. When equating on the both sides, we get gamma of Hy plus curly Hz by curly y is equal to j omega epsilon of Ex, and similarly for Ay we will get gamma of Hx plus curly of Hz by curly x equal to minus j omega epsilon of Ey, and for the Az we get curly Hy by curly x minus curly Hx by curly y equal to j omega epsilon of Ez. Similarly, for the second Maxwell equation, that is del cross E is equal to minus omega mu of H, we will solve it again in the similar fashion, and we will again get the coefficients of Ax, Ay and Az on both left and right hand side, which are shown over here in the equation 6, 7 and 8. Now, after obtaining these equations, we can obtain the values of Ex, Ey, Hx and Hy in terms of Ez and Hz. For example, if we take the equation number 7 and we obtain the value of Hy from here, and if we substitute this value of Hy in our equation number 3, that is over here, then we can see that this Hy is now obtained in terms of Ex and Ez, and when we substitute it in the equation number 3, the whole equation will be now converted into the form of Ex, Ez and Hz. It means by taking the Ex terms on the left hand side, we can obtain the value of Ex in terms of Ez and Hz. I have done this in the next slide. The value of Hy from the equation 7 has been obtained as gamma Ex plus curly Ez by curly x divided by j omega of mu, and when I have substituted this in the equation number 3, I got gamma square by j omega mu Ex plus gamma by j omega mu curly Ez by curly x plus curly Hz by curly y equal to j omega epsilon of Ex. Solving it further, I will get the solution as minus gamma by curly Ez by curly x minus j omega mu curly Hz by curly y equal to Ex of omega square mu epsilon plus gamma square. Now we can substitute this value equal to a constant named here as h of square. So by substituting this value as h of square, we get the value of Ex as minus gamma by h square curly Ez by curly x minus j omega mu by h square curly Hz by curly y. So from here you can see the Ex has now been written in the form of Ez and Hz, where Ez and Hz are nothing but the values of electric and magnetic field in the direction of the propagation. Similarly, we can obtain the values of Ey, Hx and Hy in terms of Ez and Hz. These equations gives us the relationship of the field components within a waveguide. Now, if we have to derive it for the TM wave or for the TE wave, as we know, in the TE wave, the transverse electric components are there. It means the Ez component must be there if it is propagating in the Z direction. And similarly for the transverse magnetic field, Hz component should be 0. So we can substitute the values of Ez equal to 0 and S equal to 0 for the TE and the TM wave, and again we can obtain the values of Ex, Ey, Hx and Hy. Similarly, from here you can also conclude that in a TEM wave, if both the Ez and Hz are equal to 0, then all the four components of the field of electric and the magnetic field are reduced to 0. It means it will not exist inside a waveguide. So this has been shown in the next slide, named here as the modes of the propagations. Now in the TEM wave, as these two components are 0, we can say that this mode cannot propagate inside a waveguide. Similarly, in the transverse where the Ez is equal to 0, called as the TE mode, the electric lines of flux are perpendicular to the lines of the waveguide. And the TM wave, where Hz is 0, the magnetic lines of flux are perpendicular to the axis of the waveguide. And there is one more mode called as the hybrid mode, or the HE hybrid mode, in which all the components will exist. So now let's discuss the propagation of the waves in a rectangular waveguide. As in the rectangular waveguide, we can see that there are two dimensions A and B along the x and the y axis, and the propagation of the wave is in the z direction, shown here with this. And this waveguide is assumed to be filled with air as a dielectric. So the wave equations for TE and the TM waves are given as del square of Hz is equal to minus omega square mu epsilon of Hz, where TE it is Ez is equal to 0 for the TE wave, and similarly for the TM wave where Hz is 0, the equation is now written as del square Ez is equal to minus omega square mu epsilon of Ez. Using these two equations and expanding them in the rectangular coordinate system, we get curly square Ez by curly x square plus curly square Ez by curly y square plus curly square Ez by curly z square is equal to minus omega mu epsilon of Ez in the case of TM wave. So what I have done here, if we look at the TM wave, it is del square of Ez. So del square is nothing but curly square by curly x square, curly square by curly y square, and curly square by curly z square for all Ex, Ey, and Ez. So over here I am having Ez, so I will get here curly square by curly x square for Ez, curly square by curly y square for Ez, and curly square by curly z square for Ez on the left hand side. And on the right hand side it will be minus omega square mu epsilon of Ez. Similarly, for the TE wave, we will get curly square of Hz by curly x square, curly square by Hz by curly y square, plus curly square by curly z square of Hz is equal to right hand side. So now over here we have already used that curly by curly z has been written as minus gamma. So we can write here curly square by curly z square as gamma of square. So our equation will be now reduced to curly square by curly x square of Ez plus curly square by curly y square of Ez plus gamma square plus omega square mu epsilon of Ez is equal to 0. Also, earlier we have substituted equal to h square. So again, by substituting this as h square, a constant, then our equation will be now reduced to curly square by curly x square of Ez plus curly square by curly y square of Ez plus h square Ez is equal to 0 for the case of the TM wave. And exactly similar for the TE wave, we will get curly square hz by curly x square plus curly square hz by curly y square plus h square hz is equal to 0 for the TE wave. So these are the two equations of propagation inside a waveguide in the case of TM and TE wave. The solutions of these can be obtained by solving through separation of variable method. In the case of TM wave, that is curly square by curly x square of Ez plus curly square by curly y square of Ez plus h square Ez is equal to 0, we can obtain the solution of Ez. And we have already derived Ex, Ey, Hx and Hy in terms of Ez and Hz. In the case of TM wave, Hz is 0, whereas in the case of TE wave, the Ez will be equal to 0. Now let us assume the solution of this equation as Ez equal to xy, where x is a pure function of small x only and capital Y is a pure function of small y only. Since x and y are the independent variables over here, we can write that curly square Ez by curly x square should be equal to, by putting the solution of Ez as x of y, we will get it is equal to curly square by curly x square of xy. As I said that capital Y is a pure function of y only, it means it will be a constant for the derivation with respect to the x. So I will get capital Y outside and curly square x, capital X, that is a function of small x divided by curly x square. And similarly, for the case of curly square by curly y square of Ez, I will get capital X as a constant outside and curly square by curly y square of capital Y, which is a pure function of y only. Now substituting these two equations in the TM wave, we get, means we are going to substitute this and this equation both in this part. So I will get y curly square x by curly x square plus x curly square y by curly y square plus h square xy is equal to 0, and dividing throughout by x of y, we will get this a pure function of x and this a pure function of y. and these two are adding to with a constant to give the output equal to 0. It means if two pure functions of x and y are adding to with a constant to form equal to 0, it means these individual terms must be the constants. It means we can rewrite these equations or these pure functions of x and y in terms of some constants. So I have written here 1 by x curly square by curly x square of capital X as minus of b of square, and 1 by capital of Y curly square by curly y square of capital Y as minus of a square. Now, substituting these two in the above equation, that is in the equation 16, we get minus b square minus of a square is equal to h square, and rewriting it, we get h square is equal to a square plus b square. Now, these equations, that is 1 by x curly square by curly x square of x minus equal to minus b square, and 1 by y curly square by curly y square of y, which was equal to minus a of square, are the second order differential equations, and the solutions of which are given by c1 cos bx plus c2 sin bx, and for the y it will be c3 cos ay plus c4 sin ay. Now we have seen here that C1, C2, C3, C4 are the constants which can be evaluated by or which can be obtained by using the or simply applying the boundary conditions. Now the complete solution of the Ez will become, which was earlier assumed to be equal to xy, it has now become equal to C1 cos bx plus C2 sin bx, which is the solution of x, and for the y C3 cos ay plus C4 sin ay, named here as the equation number 20. Now, similarly for the TE wave, when we will solve it for curly square by curly x square of hz plus curly square by curly y square of hz plus h square hz is equal to 0, we will get the solution of hz, which is again assumed as h capital X or capital of y, which is equal to c1 cos bx plus c2 sin bx into c3 cos ay plus c4 sin ay. Now let us apply the boundary condition on the TM wave. TM wave means this equation. I'm going to use the EX equation or the equation number of 20. So while applying the boundary condition, I have to understand first the rectangular waveguide. I said the rectangular waveguide will have the walls on the x and the y axis. It means for a length a on the x axis there will be a plate named here as the bottom plate, and there will be an upper plate which is separated from the bottom plate by a distance of b. It means the lower plate will have a dimension from x equal to 0 to x equal to a, where y is equal to 0, whereas the top plate is having the dimension from 0 to a, but here the value of y is b. Similarly, the left plate will have the value of y from 0 to b and x is equal to 0, and the right plate is having the value of y again from 0 to b, but the value of x is equal to 0. And we know in the case of TM wave, the electric field component in the direction of the propagation, that is Ez over here, is equal to 0. It is all along the boundary walls of the waveguide. So let us find the for boundary conditions for this rectangular waveguide. Now, in the case of the bottom plane, where my y is equal to 0 for all x from 0 to a, we can say the electric field in the direction of propagation must be equal to 0, or simply Ez is equal to 0. In the case of second boundary condition, Ez will be 0 for x equal to 0 but y from 0 to b, that is the left side plane. And for the third boundary condition, which is the top plane, x from 0 to a and y is equal to b, the Ez is 0. And for the fourth boundary condition, that is the rightmost plane or the right plate, where y is from 0 to b, x is equal to a, Ez should be equal to 0. Now substituting these all on my Ez equation, that is C1 cos ax plus C2 sin bx into C3 sin cos ay plus C4 sin ay. Let us apply these boundary conditions. When I apply or substitute the first boundary condition in my equation, I will get Ez is equal to 0 at y equal to 0 and for all x 0 to a. It means Ez will be 0 when y is equal to 0. So by substituting y equal to 0 over here, I will get cos of 0, which is 1, and sine of 0, which is equal to 0. So I will reduce to C1 cos bx plus C2 sin bx into C3. And it is true for all values of x from 0 to a. It means this term cannot be equal to 0. Only term which can be reduced to 0 over here is C3. So we'll come to get the solution of equation number 20 into a reduced form equal to Ez equal to c1 cos bx plus c2 sin bx. And as c3 has been reduced to 0, so this term will be removed and will be left with only c4 sin ay. Now let us apply the second boundary condition, which states that Ez is equal to 0 for x equal to 0 and for all y from 0 to b. So when we will apply this equation on my equation number 22, or the reduced equation of Ez, I will get x equal to 0. So when I substitute x equal to 0, cos 0 will be 1 over here, sin 0 will be 0, and as y is changing from 0 to b, I will uh, keep it as it is. So I will get here c1, because this term has been reduced to 0, it is only left with c1 c4 sine of ay. And as this c4 sine ay cannot be equal to 0, we can conclude that c1 is equal to 0. So we'll get c1 equal to 0, and our reduced equations now being c2 sine bx into c4 sine of ay, named here as equation number 23. Now let us apply the third boundary condition, which states that Ez should be equal to 0 for y equal to b and for all x 0 to a. So when I substitute Ez equal to 0 on the left hand side, my y should be changed to b. So it is now c2 sin c4 sine a of b. Instead of a, I will write here a of b into sine of bx. Sine bx remain as it is because its value is changing from 0 to a. Now, over here, C2 and C4 cannot be equal to 0, as we have already obtained from the previous two boundary conditions. So it means either sine A of B should be equal to 0 or sine B of x equal to 0. X is taking the values from 0 to A, so it is not feasible again to make it equal to 0. Means only possibility over here is that sine of AB should be equal to 0. Now sine of AB becomes equal to 0 only at the multiples of pi, or you can simply say the value of pi should be equal to n of pi, where n is a constant from which can take the value from 0 to infinity. Therefore, you can obtain here that capital A is equal to n pi of b. Similarly, while we are applying the fourth boundary condition, which states Ez is equal to 0 for x equal to a and for all y 0 to b, in my equation number 22, I will get the values of Ez is equal to 0 for C2, C4 sin B, A sin A by. Again, C2 and C4 cannot be equal to 0. The only possibility over here is sin B of A is equal to 0. Substituting to it equal to 0 and obtaining the value of B, we will get B is equal to m times pi of A. The important thing to look over here is that both A and B are here in the multiples of pi, but the m and n are used here to show, to give that they may have the different values of m and n. It means if n is value 0, there may be a possibility that m will have a value 0 also, 1 also, 2 also. So just to differentiate them, we have used here two different constants. Now the complete solution, which has been given by c2 c4 sin bx into sin ay, we can substitute the values of capital A and capital B over here, which has been derived from the boundary equation number 3 and 4. We can get that Ez has now come out to be equal to c2 c4 sin pi by a m pi by a into x sin n pi by b of y. Now c2 and c4 are simply the constants, so we can reduce them into a single constant, and we can get, and as we can using here the z-axis as a direction of the propagation, so definitely over here the time axis will be there, and we can add here e raised to power j omega t and the propagation constant also in the direction of the z, given as e raised to minus of gamma z. So our complete solution of Ez will be this, where c2 c4 can be reduced to a single constant, that is c. So our overall result, or the overall Ez solution, is c sine m pi by a x sine n pi by b of y e raised to power j omega t minus gamma of z. This is the only solution of Ez in the case of the TM wave. Now, for the TM wave, we have already derived the values of Ex, Ey, Hx and Hy by simply substituting the value of Hz is equal to 0. So it means when I will substitute these values of Hz, as in the case of Ex I have discussed here, which was Ez is this one. So Ex is now, by substituting the value of Hz equal to 0, has been reduced to minus gamma by h square curly Ez by curly x. The important thing to note over here, this equation I have obtained from the starting equations, where I have written Ex, Ey, Hx and Hy. So by simply substituting Hz, I have obtained this. Now, the only thing over here is Ez. We have obtained the value of Ez by substituting the value of Ez over here. I can get the value of Ex as minus gamma by h square into C, which was a constant, into m pi by a cos m pi by a x sine n pi by b y e raised to j omega t minus of gamma z. And similarly, we can get the values of Ey, Hx and Hy in the case of TM waves. And these were these all equations. So at the end of this lecture now we can conclude that we have derived the general solution of TM, TE and the TEM waves, and we have analyzed the propagation of waves in a rectangular waveguide, where we have concluded that TEM wave does not exist inside a rectangular waveguide. Thank you.